You're listening to a podcast from 702 and Cape Talk.
702 and Cape Talk.
The Naked Scientist.
Chris, good morning.
Reedy!
It's wonderful to be with you. Really love it.
It's been a while, hasn't it?
It has been a while. I have been listening, but it's not the same. So I'm glad I'm sitting here today. Let's start here. A story about knees and the nose. Where do the two meet?
Well, the headline on this one is, if you need some new cartilage, then you need to look nose further than your own nose, because scientists in Switzerland have taken the cartilage, or a small sample of it, from a series of patients' noses, because the reason your nose is spongy and can move around is because it's not bony, it's made of nasal cartilage. They have taken a tiny biopsy from the noses of 10 people who had knee injuries to the cartilage in their knee, which was causing them problems with movement and pain. The biopsies were broken up to get the cells out called chondrocytes, which make cartilage. The scientists, this is Ivan Martin and his colleagues, incubated the samples in a growth medium for a couple of weeks before about 50 million or so of these cells they'd grown in the dish were then added to a special matrix, which is like a support scaffold. They were grown there for another 2 weeks to make a patch, and this was then cut to the right size and implanted surgically into the knee of the individuals who had the knee injuries. So they all got patches made from their own cells and their own nose, and then the doctors followed them up for 2 years. And in all cases, the individuals got much better function in their injured knee and reported an improvement. Now, obviously, one has to be sceptical and cautious about this because there are only 10 patients in this trial, which is published in the Lancet Medical Journal this week. But at the same time, they did do follow-up studies, and it does look like these nasal cartilage cells are very good at adapting their function and taking on the role of becoming articular cartilage, the stuff that makes a sort of anatomical Teflon, a low friction coating over the ends of bones so that they can slide past each other easily in joints. And joint problems are big business. 2 million people at least around the world have cartilage problems in their knees because of trauma injuries every year. And so this could be one very neat way to repair them using a patient's own cells.
Fascinating. All those people with knee injuries from running, of course, I've got a vested interest in that. You may have found that one interesting. Thank you very much, Chris. Let's go to Joy in North Riding. Joy, good morning.
Good morning, Reedy. How wonderful to hear your voice
Thank
again.
you.
Good morning, Chris.
Hi,
Chris,
Joy.
what I want to know is, has any research been done into young women today having miscarriages? Because every second person I hear about who gets pregnant seems to have a very early miscarriage. Whereas years ago, if you got pregnant, you were pregnant, I think.
Hi, Joy. Well, I think there's a number of things to sort of unpack out of this. One is that it can't be that common in terms of population growth, because there are now 7.2 billion people here on Earth, and the human population is growing pretty healthily, and some would say to the detriment of planet Earth. So the net direction is in terms of population growth. So more people are having babies than not having babies. In terms of whether or not this is really more common, one also has to bear in mind that the circumstances have changed, and we tend to be much more open about what's happening to us medically. We're also much better at diagnosing ourselves as being pregnant. Years ago, there were not pregnancy tests. People just missed a period, and they thought, well, I might be pregnant, but I might not. Nowadays, people know pretty early, and they're much more frank and honest, because they know that if you have a problem like this, it does happen to people, it is frequent, it is common, and you can get some help and support for it. So I don't think there's any evidence that this is becoming a lot more common all of a sudden, but probably talking about it and sharing the information and getting support from each other probably is becoming more common. And yes, there are certain medical conditions that do make miscarriages happen, and you could argue it's sort of nature's way of making sure that the baby that does grow to term is a healthy one, because most miscarriages that happen early in pregnancy are probably because a baby would be non-viable from a genetic standpoint, because the mixing and matching of genes that goes on when a sperm and an egg meet, fertilize and make a potential life, sometimes that process goes awry and it leads to an inviable conceptus, a baby which is not going to be genetically able to function, and so those pregnancies tend to fail very early on. And one could argue that's probably a better outcome, because someone doesn't want to go all the way through 40 weeks of pregnancy and then have a terrible outcome at the end of that.
Absolutely. Let's go to Tinus in Kempton Park. Good morning.
Morning, guys. Just quickly wanted to find out from you. I've got a family member with muscular dystrophy. Now, last night we read a thing that there's a new test that was done on rats recently that shows an improvement in it that actually halts the progress of that. My question is, why do they specifically use rats in lab trials before taking it over to any other species?
Okay, why do they use rats in lab experiments, Chris?
Sure thing. And also, what is muscular dystrophy?
Yes.
Well, muscular dystrophy is a very, very common condition. It's a common X-linked condition. What this means is that the gene that causes muscular dystrophy, one of the most common forms is what's called Duchenne muscular dystrophy, after Duchenne, the French neurologist who first described this. The gene dystrophin is carried by the X chromosome. And because ladies have two sex chromosomes, two X's, if one of them doesn't work properly, it's not such a problem because they have the other X chromosome, which can have a healthy copy of the gene on it to make up for the problem. If you are male, you only have one X chromosome because your other chromosome is a Y, that's what makes you a male, and therefore if you have an unhealthy copy of your dystrophin gene on your X chromosome, then you are only able to use that dysfunctional or damaged gene. You have no alternative backup, so therefore you do get affected. So diseases on the X chromosome have an excess number of affected males in the population, and that's why they're called X-linked diseases. Now, in terms of treating these diseases, they are very complicated disorders and they are complicated to treat. What one doesn't want to do with someone who already has a disease which is affecting their life in a serious way is to make them any worse. And so what doctors do is to try to make a model or a representation in a non-human context to test out theories, to test out potential therapies and test out outcomes before they translate the therapy into humans. Because if we get it wrong, especially when you're doing things with genetics, you could affect the individual and also the children of that individual. So it's very important that this is done carefully, respectfully, and very, very much safely before you go anywhere near a person. And because rats are mammals, they have a very similar physiology to us, they have a very similar genetic makeup to us, and the way their bodies work is very, very similar to us. They are a good initial starting point for looking at some of these sorts of diseases and possible treatments and therapies for them to make sure that these things have some chance of being safe, and it's therefore worth the risk of trying them in a person in the first instance.
All right, I see your calls, Glenda, Hamilton and Ernie. We'll get through them as soon as we've done this.
702 and Cape Talk.
The Naked Scientist.
Let's go to Glenda in Bedfordview. Good morning to you, Glenda.
Hi, good morning to you both. I've listened with great fascination at Chris's introduction on the cartilage growth and transplant. My question is, do you think this would be utilized for scaphoid fracture in the wrist going forward? Because currently the treatment is rather unsatisfactory for a scaphoid fracture.
Oh, hi, Glenda. First of all, for people who are not aware what a scaphoid is, that your wrist has a whole bunch of little bones in it, the carpal bones, and the scaphoid is one of them. And the problem with the scaphoid bone is that when you fall over and land on your outstretched arm, you can break the scaphoid bone, and it's an oblong-shaped bone, and the end of the bone gets its blood supply and nutrition from the end closest to you. And the supply comes through the outside layer of the bone. So if you break the bone, you can interrupt the blood supply, and this means that the end of the bone ends up being deprived of its blood supply, and it can die back, and you can have necrosis of the bone tissue, which can lead to arthritis, it can lead to loss of function, and it's painful. Now, in terms of what they've done here at the University of Basel at the moment, this is the Ivan Martin Lancet paper I was talking about at the start. This is really intended to remodel cartilage. At the ends of our bones are layers of slippery material. It's called articular cartilage. It's made by cells called chondrocytes, which produce a whole host of slippery molecules, including glycosaminoglycans, which are like a sponge. And they soak up lots of water, they take up space, and they're very, very low friction. So the bone ends slide effortlessly over each other. This is worn away or damaged in injury or by the process of osteoarthrosis, which ultimately leads to deforming joint problems. And there are some inflammatory conditions that will also damage your cartilage. And when you end up with bone rubbing on bone, it's excruciatingly painful. Now, with the trauma cases, in these people who've had damage to their cartilage, putting new cartilage in, which is what this group have done, it is a good idea because it's a way of restoring what's been lost. Trauma which causes fractures is a slightly different problem, but if you then end up with arthritis because of that fracture and damage to the cartilage, anything that can be used to produce new cartilage surfaces to resurface bones, that is a good thing. So it's possible that in the future this sort of technology, or growing new cartilage in the laboratory in the way these doctors are trying to, will help us to sort out arthritis arising as a cause of bone fracture or trauma, which is, and this sort of arthritis is common.
All right, who came in first? I think it was Annie in Cape Town. Good morning.
Good morning. Good morning, both of you. I'm 50 years old. I turned 50 earlier this year, and I've always been a very avid runner and cyclist, and fairly competitive. And when I was still cycling, I did a lot of max tests, and took it very seriously at one point, although not professional. And I've managed to push my heart rate up to, let's say, for example, 192 when I was about 30 or 35 years old. And about a year ago, I did one of the runs here over the banks here in Cape Town, and I managed to push my heart rate up again. I was running with my son in the running pram, and I was managed to push my heart rate up again to about 192, and it made me immediately concerned. Is that the right thing to do when you're 50 years old, pushing your heart rate to that level? And if it is okay, is it something that you can do maybe once a month, or is there a frequency that is safe or not safe?
Okay.
Well, I was interviewing a gentleman because we went to the British Heart Foundation sponsored British Cardiovascular Society conference in Manchester in June this year, where lots of heart doctors all get together and they share good practice, they talk about their research, and they talk about new treatments. There was a guy there talking about what he dubs the mammal, the middle-aged man in lycra, and this phenomenon of people who suddenly take up exercise in middle age, and then there's a concern over whether they're going to do themselves some harm. The point he was making is that if you are fit and well and healthy, then exercise is much better for you than any other pill that a doctor could possibly invent. We don't have a pill which is anything like half as good as regular exercise. And so as long as a person is otherwise healthy and having no symptoms, then on average at the level of the population, we're not talking about individuals here, we're talking about everybody, if more people take exercise more of the time, then they're going to be much healthier than if they don't. Exercise is really good for you. In terms of an individual, I don't think it's a good idea to have a target heart rate where you say, well, I'm going to run and I'm going to push my heart rate to X, Y, Z. You should do what you feel comfortable doing, and if you start to experience ill health or symptoms, or you pick up something that does not feel right, then you should get it investigated. But that goes for anybody of any age, and so I would just enjoy your exercise, and I think it's great that you're much better shape than I am.
Yeah. Here's an interesting question here. It says, by the way, Annie, just go ahead, keep exercising, you're fine. There's an SMS that somebody wants to know, where does the intelligence of children come from?
Well, when we're born, the brain that we're born with is a compromise between our mother's anatomy and what we need to be as autonomous and independent as we can be. Let me explain. Humans have an unfeasibly big brain for the size of our bodies, and this is what gives us our ability to do the extraordinary and amazing things that we do. But there's an anatomical problem, which is that being mammals, we have to grow inside our mother's tummies, and then we have to get out. And this is why babies are born at the stage they are, and in this completely helpless state, largely, because if we allow babies to grow any bigger, their head and their brain will become insufficiently small to get out of their mum the normal way. So when we're born, we're therefore very dependent on our mother to look after us. But scientists have speculated on, well, there are some things that babies know how to do when they're born, and there are some things that we have to learn as we grow up. And there was a German anatomist, I think his name was Flechsig, who about 100 years ago or so was very interested in this question, and he studied the structure of the brain. He was looking in smaller animals, he wasn't doing this in people, but he was very interested in some of the things that animals know how to do when they're born and some which they grow up learning how to do. And he found that the pathways in the brain which are critical for you to have independent survival when you're born, things like breathing, control of your heart rate and blood pressure, sleeping, waking, drinking, crying, those sorts of defense mechanisms and those protective mechanisms and survival things, they were all activated first, and they were laid down. There's a plan of how the nervous system should form, which is executed during embryonic development, and certain things connect to each other and make these pathways, so you're born with certain things that you automatically know how to do. And it's the same with virtually all animals, and even, you look at plants. Plants know how to germinate their seed, send a shoot in the upright direction, send a root in the downward direction, make things like chlorophyll to make their leaves green. There are genetic programs that cause cells to communicate and organize themselves in 3 dimensions in a certain way. It's no different in your nervous system. And then as you grow and evolve and age and learn things, you then superimpose on that rough map that forms when you're first born the knowledge and experiences of learning. So a good example of this is seeing. When a baby's first born, the visual system is quite primitive, and the eyes connect roughly to the right bits of the brain, but they don't see terribly well to start with, and it takes the input from the world and seeing and experience to refine and adjust those connections in the brain so that you then see clearly in the rest of your life. And it's the same in all animals. So rough map, initially determined genetically, and then life experiences superimposed on top.
Here's an SMS for the Naked Scientist. What causes that funny feeling when you go down an incline and up quickly, like a roller coaster or a dip and hump in the road? That's from Kian.
Yeah, I mean, my son always says when we go over the humpback bridge near our house, it makes a certain part of his anatomy feel a bit strange. And I remember having the same experience when I was little. And the reason for this is that when you are going along and you suddenly go into free fall, the internal organs in your abdomen, your intestines, your liver's very big and heavy and so on, they are momentarily weightless. They're normally hanging inside your abdominal cavity, supported by various ligaments and the peritoneal space and the muscles. When there's weightlessness, these things lift and it changes the loading and your experience, the feeling inside of how things are under tension or being stretched and pulled around temporarily. And then when you land again, they carry on going after you've stopped. So they stretch everything for a little bit again. And that's what is producing these rather bizarre sensations as we go flying over humpback bridges or going down roller coasters. It's your innards moving around, and you have a lot of sensors sensitive to vibration and stretch in your abdomen, and they're all being tickled, and they're telling your brain that they're sensing these strange things that are unusual and that you're not accustomed to feeling until you go into one of these roller coasters or over a bridge too quickly. And that's when you get those funny feelings.
Chris, time just went by. I had such a great time, and I hope we can do this again soon.
Oh, so do I. It's been great fun. Cheers, Reedy.
Thank you so very much. That's The Naked Scientist, everyone, and we're going to podcast this. And I'm laughing at the SMSs. Can't you keep The Naked Scientist for longer? Guys, he's got a life. He's working. He's teaching. He didn't get this title, Naked Scientist, for nothing. But he generously gives us his time every single Friday. But I do know that he is very, very busy. But we look forward to Fridays where we get a little cleverer than we were when we woke up. We're going to podcast this one.